Hello and welcome back to day 6. I don't want to be spoilery, but we're going to get our first instance of brute force is slow. Not necessarily slow enough to stop us from using it, but slow. So let's dive in. All right, so the historians use their fancy device again, this time to whisk you all the way to the North Pole in the year 1518. Okay, you still have to be careful of time paradoxes, so it'd be important to avoid anyone from 1518 while the historians search for the chief. Unfortunately, a single guard is patrolling this part of the lab. Maybe you can work out where the guard will go. All right, so you'll see a lot of puzzles like this in Adventive Code, where you have a map of things to do, right? You have a grid, and you have to manipulate the grid in some way. It's a very common thing. So this is our first sample data. Okay, guard is heading up. Any obstructions, crates, desks, alchemical reactors are shown as a hash. Lab guards in 1518 follow a very strict patrol protocol, which involves repeatedly following these steps. If there's someone directly in front of you, turn right 90 degrees, otherwise take a step forward. So he walks up, 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 hits this, turns right, walks right, hits this, turns right, goes down, 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 hits this. Okay, so far so good. Turns left and then up and then across and then down and then over and then up and then across and then down. All right, that makes sense. And then you're going to fall off the board. Falling off the board is going to be our end case. Now, you just watch me do that with all the mouse, but here we're going to mark all the spots that the guard visited with an X. We need to count how many of those distinct spots the guard visited. Okay, so sounds good. Let's get started. I think what we're going to start with is we're going to start with the board. Yeah. Class board tests. And let's see. Let's say, what do we want to store about the board? We know that the board clearly has, Yeah. All right. Well, let's start just thinking about exactly what we want to know, right? Based on the problem, we want to know where's the guard? Where's the guard? Okay. And what we'll do is we'll do our standard give you input like this. Okay. So let's do 1, 2, 3, 1, 1, 2, 3. Okay. That'll be our first board. Nothing super exciting. Then we're going to say guard location is board guard location. Cert equal. Let's do it like this. Just so our numbers are different, right? So the row is going to be 1, guard location row. And then guard location column. Right? So row 0, row 1, column 0, column 1, column 2. Pretty straightforward. Okay. Obviously, this isn't going to compile. You can consider failing to compile to be your first version of a unit test, really, if you'd like. I don't think that's all that important, but here we go. We failed to compile. So what we know we need is we need a constructor, board text. Then we need int row, int column, guard location. Let's do it this way. Throw new invalid operation. think that's all we're going to need to get this to compile and then watch our test fail. So there we go. Oh, right. I forgot I put this on verbose mode. Let's turn that off for a moment. You'll see why we want that in a moment. All right, so there we go. Our part 1 and part 2 are skipped. Our operation is invalid. We also want to know the direction they're facing, right? Now that I'm thinking about it. So our location direction. Interesting information to know, right? Char direction. Okay, so what is it going to look like for us to... Big D. Okay, what's it going to look like for us to parse this board? The reality is that character array is going to be our friend again, right? So we're going to take board text, select, a line. We're going to do line. Oh, this isn't a... We're going to do first, we're going to do a split on R, come on, or N, and then string split options, remove empty entries. Then we're going to select for the line. You're going to do it to a character array. Then we're going to turn that whole thing into an array. And that's going to be our board. All right, so that's our board. First thing we need to do then is we obviously need to find the guard location. So we'll do this. We'll say for, let's see, for row is 0, row is less than board length, double plus row. For column is 0, column is less than board sub row length, double plus column. We need to know what are all the directions that this thing could be facing. So let's start out with a hash set of char for directions, right? This is not going to stick, but this is where we're going to start. Okay, so those are our directions. And we'll say if directions contains board row char row call. Yep, I actually put 2 parentheses there and then deleted one because God only knows why. Okay, if that's our place, then what we want is we want a guard location. So let's go ahead and stash this guard location. Okay, and this can now return the guard location. Okay. And we're going to say the guard location is row, column, and board of row, column. And then we're done looking because there's only ever going to be one guard. Okay, so that I think should be enough for us to get this working. Let's go ahead and run that test. Okay, looks good. All right, what's the next thing we need to do? We need to be able to move the guard. Take an action. That's what we need to do. Take an action, right? Public void, take an action. Take a single action. We don't know exactly what that action is going to be yet because we don't know where the guard is with respect to all the things that are around it. But what we can do is we can take this same board. We can say board, take an action. Right? And then we can say, okay, now tell us where the guard is after all of that. Okay. So let's do that. The guard should end up here, right? So that's going to be our row of 0. And still facing the same direction because did not hit an obstruction. Okay, so what we need is take an action. Void take an action. We can row new not implemented. Okay. That'll get us our not implemented because we tried to take an action, which didn't work. Okay, so that's good. So the only thing we really have to do now to make this work is walk forward. We don't have any obstructions yet, so let's not worry about obstructions. But we do need to know how to move based on the direction that we're facing. So here we go. We're going to now change this to a dictionary. And we're going to say you're going to return D row, D column. Okay. So this is now going to look like this. Okay. Oh yeah, and I can do this. Okay, so when we're going up, we want to go up a row and change no columns. For going right, we want to go right without changing any rows, so add a column. And here we want to go down, so that's +1, and here we want to go left, so that's -1. Okay, what have I done wrong here? Probably can't do that like that. Probably need to do it like this. New parentheses. Here we go. Okay. So that should send us in the directions. So now, instead of saying directions contains here, we're going to do directions.contains key, because those are now our key, right? So that's where our guard is. Let's go ahead and now just move the guard, assuming the guard can move. That's a reasonable thing to do first off, right? So let's do that. Guard location, let's see. So var next is directions dot, let's see, directions of the guard location direction. Okay, and then we're going to say guard location row plus equals next D row. Guard location column plus equals next D column. Okay, so that's our movement. That's pretty simple, right? So there we go. That's looking good. What's next? Next we could say, what happens when the guard leaves? Okay. Well, I don't know. What do we want to say when the guard leaves? So we can take an action, and then the result would be that the guard location gets updated with some sentinel values, right? That's one possibility. It's like, you know, your row and column are -1. You're off the board. You're no longer around. That's probably a reasonable thing for us to do. So let's go ahead and do that. So we're going to take 2 actions, and then we're going to say that that's what happens. And we really don't care what direction they were going when they left. Okay, so that's going to fail because, of course, I expected -1 and got 2. Because we didn't look to see whether or not we rolled off the end, right? So we rolled off the end in terms of the row, but not in terms of the column. And then we're going to say if guard location row is less than 0, or guard location row is greater than or equal to board length, then the guard location, let's do this like this. All right, and then we'll also do, or the guard location column is less than 0. Now, I realize I'm implementing more than I need to. That's just purely doing this for time. You could do this in incremental steps if you wanted to. Smaller steps are always better. But trying to keep these videos at a reasonable length. So, okay, so if that's going to be the case, then the guard location row is -1. The guard location column is -1. We really don't care about the direction. We'll go ahead and leave it there. Okay, so now what? So that's good. That passes. I think I also want to know if the board is, if we're done. That's kind of what I want to know here is, are we done? And this is one way of knowing that we're done, but does the board need to know that we're done, right? Should I be able to say assert equal, or assert true board finished? Okay. Do I want to do that? And if I do that, then I want this to also be false, right? So let's do that. Obviously that won't compile, but what we can do is we can say finished, public bool finished. We'll start with false. That will mean our guard leaves test is now broken for finished. And we're going to say guard location row equal to -1 and guard location column is equal to -1. Okay, so now we know that we're done. There's an edge case here. What happens if we try and take an action after the guard is gone? Take an action after we're done. After we're, yeah, I can't put apostrophes there. All right, so what happens if I try and take this third action? I think what I want this to do on this third action is throw. So what I really want here is var ex is record exception or take an action. Of course, you're going to tell me I don't need the lambda, right? And then I'm going to say assert not null ex assert is type invalid operation exception ex. And what I would normally do with exceptions is say guard is already gone. I'd check the messages. I like to do that. Okay, so that test is going to fail, right? We got a value is null, meaning we didn't throw the exception. So in take an action, then what we want to do is we want to say if we're finished, throw new argument. Nope, throw new invalid operation exception. Guard is, what did I say the message was? I forgot already. Guard is already gone. Okay, guard is already gone. So there we go. We're now throwing. So if you try and take an action when there's no action to be taken, it throws, which is good. We appreciate that. All right. So the last thing we need to do, according to the be quiet, phone. The last thing we need to do, according to the instructions, is we need to, sorry, not the last thing. The next thing we need to do is we need to take obstructions into account, right? So our next test then will be when hitting obstruction, guard turns. Okay, that's the next thing we're going to do. So let's take this board. Okay, and let's put an obstruction here. Okay, and so then we're going to go grab the location again, right? And our location should not have changed from before. We are still in row 1, column 2. However, our direction will now have changed. So our direction will now be guard location direction. Okay. So that's obviously going to fail, right? Because we just walk through the obstructions right now. We don't even know that they're there. So let's go to take an action and let's say this. If let's see. So I don't want to just go and increment these willy-nilly yet, right? So let's say next row is guard location row plus next D row. And we'll say the next column is the guard location column plus next D column. So where would the guard go? We can move these into next row, next column. Okay. If the board at the next row and the next column is an obstruction, right, then what do? What we do is we want the location, the direction to be next, next direction. We don't have that yet. But what we want to do here is sort of turn ourselves and then not move, right? So that means we need to now expand this to now include char next direction. Okay, so let's go ahead and throw a couple of these in here. No, that's not right. The commas go here. The next direction for you is this way, and the next direction for you is this way. The next direction for you is this way, and the next direction for you is this way. Okay. Happy with all that, although I'm, lining things up because I don't know why, because that's just who I am. Okay, so we now moved in the next direction, which apparently was a little n. Okay. That should solve this problem now, right? So let's come down here and run these. No, it does not. Guard is already gone. We got an invalid operation for what happens when the guard leaves. Well, that's interesting. Did I logicked it wrong, right? I obviously must have. The next row and next column is in, not plus equals, just equals. Okay, we got an index out of range for what happens when the guard leaves. That makes sense because we probably need to do this instead of this. We need to do it up here, right? So we're going to say next row and next row and next call and next call. And by the way, that's short enough that we can put you all on one line. And also you're done. So we need you to get out of there. So if we run off the end of the board, we're done. If we found an obstruction, we turn. Otherwise, we move. Okay, that's the right order of stuff. Let's make sure that everything's working. Okay, good. Everything looks good. So we need to test some movements. So one of the things we could do is let's turn this into a theory. All right, so we'll say our inline data is going to be, to start with, the guard direction. And then we want to know what is the expected row. Whoops. What is the expected row and column? We'll have char, direction, and expected row, and expected column, right? So down here, this is now the expected row. This is now the expected column. This is the expected column. This is the direction. And this little bit here needs to become our direction. Okay, this makes us a little ugly, but it is what it is. First, with just that one set of data, did we keep everything working? Okay, we did. So very good. So let's do all 4 directions now. Let's see what happens when we move in each direction and make sure that's working as expected. All right, so if I was going to move right from there, that would put me in 1 and 3. If I was going to move down, that would put me in 2, 2. And if I was going to move left, that would put me in 1 and 1. Okay. 1 and -1. 1 and 3. If you're going right once, right? Because we were at, 1, 2. You should have gone to 3. Why are you all the way off the board? Okay, well, our edge case is not right. Did I do a greater than? Oh, yes. Board sub next row of length. That was an interesting edge case we just found there, right? Because our board is not square, which actually isn't normal for their data, but it's fine for now. Okay, very good. We're good to go. So that's all of our movements. That's all of our turning. And then we have basically everything there. So the last thing we want to do is we want to say public void records movement squares. Okay, single move. So what's the other thing we need to know is we need to know the actual squares that the guard has been in. And we need to basically track all of that. So what do we want that to look like? Let's have our board be this board again. Right? We're going to take an action. And what our board should look like is 1, 2, 3, that. 1, 2, X, right? Because remember, that's how they were showing it in the example, is X. So there we go. So there we should have 1X. So really what we're trying to do is count the X's. So we're going to say var, we'll do it up here, right? Var visit count. Sure, that's what we'll call it. Board visit count. And then we'll just say assert equal 1 with a visit count. Okay, so we don't have the visit count yet. So let's go make a throwy red public and visit count row new not implemented exception. There's our red. Let's go make it pass. We need to count the board. We need to do, we're going to use a link for this. We're going to use a select many. I'll explain what that is here in just a second, right? And then that's going to be a row. Row select. For a cell, cells equal to X, then it's 1, otherwise it's 0. And then we're going to take a sum of that. And then we're going to take a sum of that. Our select, okay, so select many. Argument type, not be inferred from usage. So row select gives me an int. And then a sum, right? Because that gives me a sum. That's an int. Then the select many should be able to sum on that, right? Why does it not know that that this is a? Oh, I know why. Do I? No, so that should be an int. Let's see if I do select. Whoops, that's wrong. That's wrong. So if I did select, what I get back is an enumerable of ints with a sum. Oh, actually, that's what I want. I want to select, not a select many. All right, because each row turns into an int because of the sum, and then I sum everybody. Okay, that's good. That'll work. We're still going to get 0 instead of 1 because, of course, we haven't actually recorded our steps. So this is when we take a step, right? So what we're going to do is we're going to say, let's see. the board at the current guard location row and the current guard location column is now an X. All right, so we need to record that step so that we can go count them later. Okay, so that's pretty good. So if we were to then say, do that, do that while we're not finished, right? That'll be sort of the next step, right? So let's do this. Let's say public void. Count all steps. Let's take this board. All right, we're going to say while not board finished, take an action, right? And then we're going to get the visit count and check it. So in this case, what we should see is we stop in 2 spaces. My brain says it's not actually going to happen, but we'll see. Right, 2 and 1. And the reason for that is we marked the movement space down here, but up here, when we leave the board, we also need to mark the space. So what I want to do then is I think let's invert these for just a moment and make sure that we're not, okay, so nope, that's not good. We can't do that. Okay, so then we basically need to say that here we're going to record the location as well. Actually, we can record it up here because even if we're, even if we're going to turn, right? Even if we're going to turn, we know that the turn doesn't matter. We've definitely been there. So anywhere where the guard has been can get marked. That's actually totally fine. We'll just mark it up there. Okay, so that's good. So we've now proven that we can turn when we see an obstruction. We can move until we get off the end of the board, and we can record every space where we've been. I think that's all we need to pass part 1, right? So let's go write the test. So we're going to say the board is new board file.readAllText from the file name, because it parses it automatically. All right. And then we're going to say while not board finished, board take an action. All right. The result is going to be board. What was it? What did we call that? Visit count. Okay. Get out of there, extra semicolon. Okay. Oh, yeah, well, we're still skipping the tests, so that doesn't help. Are we actively recording 41 steps now? Okay, it looks like we are. So that's the data 1 data, right? That's the first data that they gave us. The data 2 data, what you can see here is that showing here that we are on 131, and then if I go all the way to the end, we're on 131. So this is a 130 by 130 grid. So it's a very large grid, but basically the same kind of layout. Somewhere in here is embedded a guard. There it is, right there, kind of in the middle. So let's see what happens here when we try it with our other data. Okay, we got success. All right, that's good. All right, I'm going to turn the verbose mode back on. And the reason I turned the verbose mode on is because it watches me do each test and gives timings. And so what I'm kind of interested in here is the part 1 version, right? So that's, 1 millisecond that it took, almost 2. And for the full set of data, the other one was a little slower. I think that's just because we're accounting for maybe reading that file for the first time. I don't know. But we're still pretty quick. So let's go ahead and turn verbose mode back off. Not necessary for the moment. We can just see our successes. Okay, let's go back and now look at part 2. While historians begin working on the guard's patrol route, you borrow their fancy device and step outside the lab. From the safety of a supply closet, you time travel through the last few months and record the nightly status of the lab's guard post to the walls of the closet. Returning after what seems like only a few seconds to historians, they explain that the guard's patrol area is simply too large for them to safely search the lab without getting caught. Fortunately, they are pretty sure that adding a single new obstruction won't cause a time paradox. They'd like to place the new obstruction in such a way that the guard will get stuck in a loop, making the rest of the lab safe to search. So they want to minimize the amount that the guard is allowed to walk around. So to have the lowest chance of creating a time paradox, historians like to know all the possible positions for such an obstruction. The new obstruction can't be placed at the guard's starting position. In the above example, there are only 6 different positions where a new obstruction would cause the guard to get stuck in a loop. So the simplest one is to place an obstruction right here next to the guard. So the guard walks all the way up, turns, walks over, turns, walks down, turns, walks this way, turns. So literally a single loop. Okay, so that's not bad. Every one of these gets a little bit more complex. So put the obstruction here. We go up and around and over and over and over and down and down. And so here's the loop here now, right? That little smaller square. And then here, the loop that ends up here is between these 4 guys. So we get into that loop. And then the loop that happens here is between this, 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 and this. So this is our final loop here. And then this one is, the loop here is a longer loop. It's not a simple square loop. It's actually the whole thing, right? So up, down, and around, and up, and over, and down, and up, and up, and around. So this is now a bigger loop. And then here, we get a very similar thing where we basically are looping around the whole thing. So it doesn't matter what you choose to use as an obstacle, so long as you and the historians can put it in a position without the guard noticing. One thing is having enough options. I can find one that minimizes time paradoxes. In this example, there are 6 of them. You need to get the guard stuck in a loop by adding a single obstruction. How many different positions can you choose for this obstruction? So our first version is 6. Okay. So that's this. Now, what do we need for this board to be able to take a loop? Basically, what we can do is we can add an obstruction basically anywhere on the board, and except for the guard's location, and then just run it and see if we can find a loop. So how are we going to find a loop? The answer is pretty much, the simple answer is if you record every place and direction that the guard has been, if they're in that same place and direction again, you've hit a loop, right? Because there's no way around it. If you're going the same way, then, you're going to be back here again because you were already here once. So interestingly, this version is not necessarily about tracking the X's. Could be about tracking instead the directions that you were facing when you were in this spot. So can't really do that in the board itself because obviously you could have more than one direction for every spot. Also, as it turns out, you can slightly optimize the memory storage here by not recording every position they're in, but only recording the position they're in every time they have to turn, right? So if we look here and we say, actually this one is okay, but it's like we come up here and you were facing north and you had to turn. So we could say you were north and had to turn here. And then you go here and say, well, you were facing east and had to turn here. So we could reduce the amount of information that we're storing and just be worried about the turns. Because even though every single step along the way is valuable information, the turns are really the way we do it. But we'll do it the less optimal way because I think it's easier to start, and maybe that's an optimization we can come and do later. Okay, so given this board, what we also need to be able to track is whether or not we're in a loop. So first of all, what does that look like given our data model? Well, finished puts us at row -1, column -1. We could do that with a different set of sentinel values, -2, -2, for example. That might be a good loop, right? And then finished could be, less than 0, and then we can do a loop actually checking for -2, -2. So let's actually, the first thing we need to be able to do is add an abstraction to a board. Because remember, we're taking the board data as is from the file. We're not going to add the abstraction to the file. We're going to add an abstraction to a board and then get it running. So let's actually start using the real data because we have examples from the website of how this is going to work. So first of all, let's just do the looping part. Act public void. Why are you up there? Can detect infinite loop, right? So our board is going to be a new board. This time we're going to start with the data that we got from the website, but we're going to add an abstraction here, right? So we're going to add an abstraction here. So that will be our loop. First of all, we have to decide, do we want the abstraction to be an O, or are we just comfortable putting it in like that? Because we know that our logic today is looking specifically for this as an abstraction. Because the other thing we could do is we could say, hey, if you're not equal to a dot, right, then that would allow us to place an abstraction in the board, be able to visibly see it if we had to look at the data in debugging to know that we got there. Okay, and then what we want to do is we want to say, while not board finished, board take an action. All right, and then we want to say assert true board caught in loop. Okay, and I'm going to go ahead and where's the other one where we finished? Take an action after we're done. Nope. Here's our what happens when the guard leaves. So we're going to go ahead and put false for caught in a loop here. And just to get this running, we'll go ahead and say public bool, not a hyperbolic function. Caught in a loop. Guard location. Oh no, whoops. Let's throw. Sorry, that's what I want to do. Throw new not implemented. So the new test will fail, and our old test will also fail because one's looking for false and one is looking for thing. Oh, and we're obviously now stuck in an infinite loop. So we obviously did not detect the infinite loop yet. Let's go and now put in this. So we're going to say less than 0, less than 0. And let's say guard location row -2, guard location column is -2. Now our other test should pass, but our new test will now still be caught in its infinite loop because we haven't prevented anything from doing that, right? So let's go ahead and cancel out of that. And then what we want is the loop detection. So how are we going to know that we have detected a loop? We can now say visited squares, right? If we have a dictionary of char to hash set of char, and say visited squares. So we'll do that, and actually you'll let me do that. So then what we're going to do is we know that what's going to be in there is a direction. No, actually, why did I do a char? This is row and column. Right, that's our key, right? So if we know that the next space is going to be a loop, if the except this is not the board that we care about. We want the, let's see, visits is going to be visited squares dot add or get. We're going to use that same helper extension function that we used yesterday from the next row and the next column. All right, and then we're going to say if visits contains our guard location direction. All right, and here I am always forgetting my second parenthesis. If we've already been here facing that direction, then we know that guard location row now is -2. Guard location column is -2. And we can return. Since we weren't here yet, we're now going to record the fact that we were here. So we're going to say visits add of our current direction, guard location direction. Okay, so this is basically saying every time we visit a square, we're going to record that fact, right? And we're going to, if we've already been there in that direction, in that square, we're obviously done because we're in a loop. Otherwise, we put it in the list so that we can detect it next time. That should be enough, I think. Okay, so 41 and 29. Oh, that's, and we got our part ones are now failing. Part ones are now failing. Well, that's interesting. I would not have expected that. The board records an X. That's okay. Visited squares, add or get, next row, next column. That is weird, right? Oh, you know what? This should be the current row and column. Right. Because we're here. We can actually do that up here. Because that does not depend on anything else. Is that our problem? No, now we're still 41, 29, 55, 34, 498. That's weird. What did we do here? Like, why? Visited squares starts out empty. It is row and column. All right, well, let's walk through this. Let's see what's going on. The only test I care about is this one. So let's only run that one. Okay. Our visited squares right now is empty. Our row and column is 6 and 4. That's fine. So our visits is empty. The visited squares now is 6 and 4, but no directions because we didn't record the direction yet. No, because we didn't record the direction yet. Well, let's move that up. That's fine because we didn't record the direction yet. I'm going to split the screen. just so that I have an easy way to go run my test down here. Okay, that did not help at all. All right. So there are no visits, right? There are no visits. So now there is a visit of up in this current location, which should be 6 and 4. There's an up. Okay. Then we get the next. All right. We know that's going to just move up. We have marked an X where we are. Oh, yes, this change. This change is what's wrong because it's seeing the X's and assuming that that's an obstruction. So we'll say this. Think I can do it like this. I can say, is this or that? Yeah, there we go. Let's run these tests again. Okay, that's better. Yeah, so this was, obviously tripping up on the X's. Okay, so that we're now able to record the loop, right? So that's pretty good. So what do we need to do now? What we need to do now, basically, for this is we are going to do this, right? I'm going to do that. Oh, actually, we need one more function. I'm not going to TDD this function into being because I need to be able to add an obstruction, right? Int row, int column, and this is basically going to be board of row and column is an obstruction, right? That's all I need. I need to be able to add an obstruction. Now when I come down here and look at what this is going to be, we have this board, right? So now instead of looking for visit counts, what we're going to do is we're going to have to start adding obstructions to find boards where the obstruction causes a loop. So what we'll do is we'll read the board once. And then we need to know where we need to know how big the board is. So we're going to say for var row is board rows 0. Row is less than board rows. Row is a double plus row. Var column is 0. Column is less than board columns. Double plus column, right? And so we need to know that so that we can walk all over those. And what we're going to need then is, let's keep this text. We'll just call you text. We're going to call this board, we're going to call this the clean board. All right, and then down here, we're going to make a new board given the text. And we're going to need basically a clean copy of the board every time. So we're going to do this where we're going to say, give me a new board. We're going to say, we need our results is not this. Our results is 0, right? And then we're going to say, while not board finished, right? Board taken action. And then we're going to say if board caught in a loop, then result plus plus. All right, that's it. And then we should have our results. So now all we need to know is how many rows and how many columns are in this board. We could probably know that without taking a clean board, but the parsing of the text is sort of irrelevantly simple, so not a problem. We're going to do columns, public int columns is going to be board sub 0 dot length, and then rows we'll put down here, public int rows, going to be board length. The other thing we want to do in this is, remember, we don't want to try and do this on the guard spot. So we have to say if row is equal to clean board guard location row, and column is clean board guard location column, and we'll just move on. That one's not worth running. Okay. Let's see what happens here. Okay, we got our 6. That's good. I'm going to... yep. Okay, let's just see if this works. Oh. Yeah, we didn't actually run 6. Let's stop skipping this and make sure we actually got 6. We did not. We got 0. That's interesting. Okay. Oh, because we didn't add the obstruction, of course. So there we go. We got 6. Very good. All right. Let's run this now. And here we have our first long running test. And this is going to take, I don't know, probably 10-ish seconds, I think. We'll see. I'm doing it a little bit differently than I did it yesterday, so we'll see. Okay, 14-ish seconds. That's a little bit more than I expected. I think that's probably because some of it was the parsing, because we're creating a new board every time, right, to parse. One thing we could do is we could clone a board, right? We could take the data that's already parsed and create a clone of it. That would be one way to get some of that time off. So let's see how that works. So instead of creating a new board here, right, what we really want to say is var board is clean board clone, right? And the value that that's going to give us by being able to clone a board is that we never have to worry about reparsing everything. So what we want to take copies of is basically all of our data. And so what we care about really is the board and the guard location. Okay. So we want to be able to create a new one of these. We'll make a new constructor, board, with character array, board, and this type is the guard location. I'll say this board is board. This guard location is guard location. That'll give us a clean copy of the board. And then for our clone function, we'll just come down here and we'll basically say, how do I get a clean copy of the arrays? We don't just want to pass it by reference, because passing by reference will give you the same arrays. And so when we start writing over top of the quote unquote copy, we'll be writing on over top of both. So we need to reconstruct the arrays, right? So the new board is going to be the board. And what we're going to do is we're going to select row to array to array. So even though we have arrays, we're now going to make sure that we get a copy, because of course to array is going to give us a copy of all the data that's in there. And then we should be able to now return a new board. With the new board, the guard location, so this this stuff can just be guard location dot row, guard location dot column, and guard location dot direction, right? That'll now take a clone. So if we come back down to our test, right, now we're okay with this. Let's see how fast this runs now. Let's see if that helped us. Is the problem memory allocation or is the problem the parsing? And how long is it going to take? 12 seconds. So we got some of the time off. But we're probably still losing time to the memory allocations. So what else could we do? Interestingly, you could take a board that has been, I think this is probably going to be our best optimization. I did not try this yesterday, but talking with some people on the Slack server, we have an Advent of Code channel on the social Slack server that I'm on. Someone had suggested that one optimization you could do was only put obstructions in places where the guard has gone. So what you do is you run the board once. You record all the locations that the guard has gone, and then determine whether or not, you know, those are the locations that you want to put obstructions in, right? Because there's no sense putting an obstruction anywhere else because the guard isn't going to hit something unless it's in one of the spots where it is. So from a data perspective, let's look at this. Let me calculate this, right? Bring calculator over here. So we have 41, and this data is 10 by 10. This is a 10 by 10 grid. So we can do that math, right? 41 divided by 100 is 41%. So that means we are only going to run against 41% of the data. This we determined was what, 130 by 130, right? Okay, so if we did 130 times 130, that's 16,900. 2262. So 2262 divided by 16,900 is 13%. So that's substantially less, right? So that should cut our time down from where we were at right now is 12 seconds. That should cut our time down to 2 seconds, right? So that's a pretty worthy optimization to try, in my opinion. So let's go ahead and try it. So first of all, we're going to have the clean board. Then the second thing we're going to need to do is we're going to have the first run board. So we're going to take the clean board and we're going to clone it, all right? And then we're going to say, while the first run board is not finished, first run board, take an action. Right, now we need to know all the visited spots. That's really what we care about. Interestingly, we have unintentionally sort of recorded all of those things already because of this, right? So we have recorded all the visited squares. So one thing I'm going to do is, before I do anything else, just to make sure that counting the visited squares is useful information, let's see if returning the visit count here, instead of doing this, let's instead do this, right? How many squares did I visit? Is that going to work? That looks like it's going to work. Okay, so that's good. So that means we don't actually have to run the board to figure out where all the X's are. Not that that was ever really an expensive part, right? Because part one was really pretty cheap. So we're still here at 12.7 seconds. Okay, so that's a good thing. So we know that that's going to work. We just need to know the list of visited squares. So pretty easily we can do this. We can say public int row, int column, array visited squares. right, is going to be visited squares keys to array. That's pretty simple. And of course, you're going to want to use the new collection expression. Congratulations on that. I don't know why that's better. I'm sure someone on the compiler team could tell us. So there's our visited squares. So what if we only run the visited squares instead of running the whole loop? So instead of doing this, right, now what we're going to do is we're going to say for each var visited square in first run board visited squares. Okay. And then we're going to say the row is visited square row, just so I have to change as little code as possible. Column is visited square column. Okay. We still want to check for this because, of course, we will have visited our initial guard location as well. So we still don't want to visit it. Let's see what happens if we run this. Okay, well, we didn't quite get down to 2 seconds, but we got down to 3 seconds. That's pretty good. And we got the right answer, which is also good. So we not only took the right answer, but we hypothesized that the only things that could realistically be obstructions for the guard are the places that they visited before. So there you go. That's a pretty good indication that we've gotten this working. There's probably more optimizations we could do with this, but the reality is that I feel like, we sort of evolved the design as necessary. We were able to see that we were working correctly, if slowly. We took a couple optimizations. We could probably do more. We could probably get this down. But these are things you're going to have to think about when doing advent of code kinds of problems, but also in the real world. Sometimes you come up with an algorithm and you're like, this is really too slow. And then you start to think about it in your head, like, what are the things that could cause me to be able to do this slow algorithm more quickly? I can promise you that there are things that we haven't even talked about yet that I did not think of, because that's just kind of the way these things work. So if you can think of one of the ways that you could have solved this problem faster, let me know in the comments. And, let's see who can get the fastest solution, because I'm kind of curious. Now, obviously, actual runtime matters based on your CPU. So we're really talking about percentages. So sort of, I'm going to put, the original code up there. I'm not going to put the optimized version there. I'll comment out the optimized version. Or maybe leave them both there. But to see, your machine, how different it is to run one versus the other, and see if you can come up with a solution that's better than the one we came up with today. That's it. End of day 6. Hopefully we will see you again tomorrow. And this video brought to you by the fact that Path of Exile 2 was really not available at all. I played for about 3 minutes, and we'll see. See you later.